We humans have always looked up at the sky with wonder. The sun, the moon, the stars, they've captivated us for millennia. But there's something else up there, something we can't see or touch, yet it holds the universe together. That something is gravity. Gravity is the force that pulls objects toward each other. It's what keeps our feet on the ground, what makes the rain fall from the sky, and what keeps the Earth orbiting the sun. It's a fundamental force of nature, woven into the very fabric of the cosmos. Understanding gravity is key to understanding how the universe works. From the smallest particles to the largest galaxies, gravity shapes everything we see and know. In this exploration, we'll journey through the minds of two brilliant physicists who revolutionized our understanding of this fundamental force: Isaac Newton and Albert Einstein. Get ready to dive into the fascinating world of gravity, where apples fall, planets orbit, and space-time bends. Our story begins in the 17th century with Isaac Newton, a legend in the world of physics. Legend has it that Newton had a groundbreaking realization when he saw an apple fall from a tree. He wondered, what force pulls the apple down? Newton's genius was in realizing that the same force that pulls the apple to the ground also keeps the moon in orbit around the Earth. He called this force gravity and proposed that it exists between any two objects with mass. This was a revolutionary idea, a giant leap forward in our understanding of the universe. Before Newton, people thought that celestial objects like the moon followed different laws of motion than objects on Earth. Newton showed that the universe operates under a single set of rules, a profound and elegant concept. Newton's apple wasn't just a falling fruit, it was a falling star that illuminated the interconnectedness of the cosmos. Newton didn't just identify gravity, he quantified it. His work laid the foundation for modern physics and changed our understanding of the universe forever. He formulated the Law of Universal Gravitation, a mathematical equation that describes the force of attraction between any two objects in the universe. This was a groundbreaking achievement that unified the heavens and the earth under one universal law. This law states that the force of gravity is directly proportional to the product of the masses of the two objects. In other words, the greater the mass of the objects, the stronger the gravitational force between them. This means that the more massive the objects, the stronger the gravitational pull between them. For instance, the gravitational pull between the Earth and the Moon is much stronger than that between two small stones. Think of it like this. A bowling ball has a stronger gravitational pull than a tennis ball. This is because the bowling ball has more mass, and thus exerts a greater gravitational force. The law also states that the force of gravity is inversely proportional to the square of the distance between the centers of the two objects. This means that as the distance between two objects increases, the gravitational force between them decreases rapidly. In simpler terms, the farther apart the objects are, the weaker the gravitational force between them. This principle is crucial in understanding the orbits of planets and the behavior of objects in space. Imagine two magnets. They attract each other strongly when close, but the force weakens as you move them apart. This is similar to how gravitational force works. Though gravity is always attractive, unlike magnetic forces which can repel, Newton's law of gravitation is a powerful tool that allows us to calculate the gravitational force between any two objects, from apples and oranges to planets and stars. This ability to predict gravitational interactions has been essential in fields ranging from astronomy to engineering. This law became the cornerstone of classical mechanics and helped explain a wide range of phenomena, from the tides to the motion of celestial bodies. It provided a framework that scientists could use to understand and predict the behavior of objects under the influence of gravity. Newton's work was a triumph of human ingenuity, providing a unified understanding of the force that governs the cosmos. His contributions have had a lasting impact, shaping the course of science and our comprehension of the universe. Section 4. Limits of Newton's theory, cracks in the foundation. For centuries, Newton's theory of gravity reigned supreme. It explained the motion of planets with remarkable accuracy and became the foundation for many scientific advancements. However, as scientists delved deeper into the universe's mysteries, they stumbled upon some phenomena that Newton's theory couldn't quite explain. One of these mysteries was the peculiar orbit of Mercury, the closest planet to the Sun. Astronomers observed that Mercury's orbit exhibited a slight wobble, a deviation from the path predicted by Newton's law. This tiny anomaly, though seemingly insignificant, hinted at something missing in our understanding of gravity. Furthermore, Newton's theory couldn't explain certain cosmic events involving extremely massive objects or those moving at incredibly high speeds. It seemed that Newton's theory, while powerful, was incomplete, like a puzzle missing a few crucial pieces. These limitations didn't diminish Newton's contributions. Instead, they set the stage for another genius to enter the scene, Albert Einstein. He would dare to question the very nature of gravity, leading to a revolution in our understanding of the universe. Section 5. Einstein's Revolution, a New View of Gravity. In the early 20th century, Albert Einstein, a young physicist with a rebellious spirit, was pondering the nature of gravity. He was not just any scientist, he was a visionary who dared to question the established norms of his time. He wasn't satisfied with Newton's explanation of gravity as a force acting at a distance. Newton's laws had dominated scientific thought for centuries, but Einstein felt there was something missing, something more profound. How could this force act instantaneously across vast distances, seemingly defying the limits of speed? The idea that gravity could influence objects light years apart without any delay seemed implausible to him. Einstein's groundbreaking insight came from his work on special relativity, where he showed that space and time are not absolute but are interwoven into a single fabric called spacetime. This was a revolutionary concept that changed our understanding of the universe. This led him to a radical new idea. Gravity is not a force acting through space but a consequence of the curvature of spacetime itself. Imagine a trampoline. This analogy helps us visualize the complex nature of his theory. If you place a bowling ball in the center, it creates a dip, a curvature in the trampoline's surface. This dip represents how massive objects distort spacetime. Now, if you roll a marble across the trampoline, its path will curve as it approaches the bowling ball, drawn towards the dip. This curvature guides the marble, much like how gravity guides planets and stars. This is a simplified analogy for how Einstein envisioned gravity. It helps us grasp the idea that gravity is not a mysterious force, but a geometric property of spacetime. In his view, massive objects like stars and planets warp the fabric of spacetime around them, creating gravitational wells that influence the motion of other objects. These gravitational wells are what we perceive as the force of gravity, guiding the motion of celestial bodies in the cosmos. Section 6. Spacetime, the fabric of the universe. To grasp Einstein's concept of gravity, we need to understand his revolutionary idea of spacetime. Imagine a vast, four-dimensional fabric, where three dimensions represent space, up and down, left and right, forward and backward, and the fourth dimension represents time. This fabric is not just an empty background, it's an active participant in the unfolding drama of the cosmos. Massive objects like stars and planets don't just exist in spacetime, they warp and distort it, much like a bowling ball on a trampoline. The more massive the object, the greater the curvature it creates in spacetime. Imagine placing a basketball on the trampoline next to the bowling ball. The basketball also creates a dip, but it's not as deep as the one created by the bowling ball. This curvature of spacetime is what we experience as gravity. Objects are not pulled by a force acting at a distance, they're simply following the curves and contours of the spacetime fabric. Section 7. Gravity as curvature matter warping spacetime. In Einstein's universe, gravity is not a force that acts through space, it is a property of space itself. This revolutionary idea transformed our understanding of how the universe operates. Imagine a beam of light traveling through space. It moves in a straight line, undisturbed by any forces, or so it seems. According to Newton, gravity shouldn't affect the light beam since it has no mass. Newton's laws were groundbreaking, but they couldn't explain everything. However, Einstein predicted that the path of light would bend as it passes by a massive object like a star. Why would light bend? This was a question that puzzled many. Because the massive object warps the space-time around it, and light, traveling through this warped space-time, follows a curved path. This warping effect is a direct consequence of the mass of the object. It's like rolling a marble across the trampoline. The surface of the trampoline represents space-time, and the marble represents an object moving through it. The marble doesn't just roll straight past the bowling ball, it curves around it, following the contours of the warped surface. This analogy helps us visualize how space-time curvature affects the motion of objects. Einstein's theory was confirmed during a solar eclipse in 1919. This event was a pivotal moment in the history of science. Astronomers observed that the light from distant stars bent as it passed by the sun, proving that gravity does indeed warp spacetime. This observation was a monumental validation of Einstein's predictions. This observation sent shockwaves through the scientific community, revolutionizing our understanding of the universe. Scientists around the world were astounded by the implications. Einstein's theory of general relativity provided a new and elegant explanation for gravity, not as a force but as a consequence of the curvature of spacetime caused by mass and energy. This theory has since become a cornerstone of modern physics, influencing countless discoveries and advancements.